Hello everyone. In this video, I'm going to be going over the 2017 Exam 3. Just going to be going through it and just giving you my logic and how I approach different problems, and I'll give some concepts and explanations to some degree as I go along. So without any further ado, let's start the first part of the exam, nomenclature. So nomenclature will be responsible for esters, anhydrides, acid chlorides, acid bromides, um, amides, ketones, aldehydes, alcohols, and carboxylic acids as well. So the first thing that we have over here, we have a acid chloride, and so the acid chloride is a derivative of the carboxylic acid, and so this is, I believe, in terms of priority, I think the acid chloride is, um, I think it's below the carboxylic acid and above other things. But don't hold me to that. I can't quite remember. But here it's the highest priority group. Okay. So here we have the parent chain is the cyclohexane here. And so this is the highest priority group. And so what we do is this is going to be carbon number 1, right? And so the parent chain for this is going to be called. So whenever you have a ring and you have the acid chloride coming off of it, what we do is we put, so here it's cyclohexane, and then it's going to be carbonyl chloride. Oops. Yes. So this is going to be the parent chain right here. Okay. And so you just add this part to the end of the name, and that's going to give us the parent chain name. Okay. I think it's one word, or I think it's 2 words actually. Yes. Okay. And then for the remainder of the part of the ring, we have to find the numbering that gets us to the ketone group the fastest. And so whenever a ketone group is not the parent chain, you just refer to it as oxo, right? And same thing goes for aldehyde. So if aldehyde and ketone are not the parent, or one of those is not the parent, you refer to them as oxo respectively where they are in the ring. And you can do this because if you have a carbonyl group that's at the very last carbon, that's going to obviously be an aldehyde because you don't have, for example, if you have a chain that's 7 carbons long, and if you have a carbonyl at the 7th carbon, and obviously you don't have an 8th carbon, so that has to be an aldehyde. So that's how that works. So carbonyl, aldehydes and ketones, you can refer to them as oxo on the parent on a chain as long as they're not the parent. And so here we have 3 oxo. Aside from this, we also have stereochemistry. So at this location here, obviously this is going to be carbon number 1. Down here is, use the pin. So this would be 1, this would be 2, this would be 3, this would be 4. And so if I go in this direction, as the arrow on this key is already going, right, this would be the R direction. And so the full name for this is now going to be, right, so it's going to be, well, I always put the numbering, but it's 1R, right, 1R, 3 oxo, right, cyclohexane, carbonyl chloride. Yes. All right. So that's, I cannot spell for shit. Chloride. All right. So that's the first one. The second molecule we have over here, we have to identify the highest priority functional group. And so the highest priority functional group here is the amide. And so when it comes for amides, we treat the nitrogen groups, right? The kind of quote unquote amines, right? They're not amines, but you know, it's kind of like an amine. We treat it as substituents. And so the way that we deal with these substituents is every time you write out the R group that's attached to a nitrogen, you put an N, and then you put the group. So you put the group name, And you do that in any number of times. So if you have 3 R groups, right, and they're all different, then this is how it would look, right? You put them respectively, and you do it in alphabetical order. So it follows the same rules. The n is basically you can think of it as a number, right? So along a chain, right, we have numbering for things. I have carbon number 7, 4, 3, 2, 1, right? But nitrogen is not a carbon. So the only way to refer to it is we put the n. And so here we can, it's like, you can think of it as just a number. So the same way I put like 4 for methyl, I put n methyl. It's just designating a location. And so I alphabetically, place those along the name, just as I would with anything else. So long story short, cut to the chase. So we have an amide, and whenever for esters, amides, anhydrides, anything that is like a carbonyl functional group, carboxylic acid, we always start numbering from the carbonyl and not, obviously this part is a substituent, this part is the parent. So this is going to always be number 1, right? So you can see this over here, this is 1. And so I don't have a choice when it comes to these. So this is 1, 2, 3, 4, and then over here I have a choice, but if you see the paths are the same. So 5, 6. Okay, so 1, 2, 3, 4, 5, 6. So I have a 6 carbon long chain, and the parent group is amide. And so what this is going to be is, right, hexane amide. Oh, hexenamide, my bad. Alright. So you drop the E and you add amide to the end. And now for the substituents. And so off of carbon number 4, we have a, right, 4-ethyl. And then we have N-ethyl, right? And we have N-benzyl, right? And so we have all these groups here, okay? And so now all I have to do is rank them. I have to just put into a name. So the first thing that's going to come first is the N-benzyl, okay? N-benzyl. And now comparing N-ethyl and 4-ethyl, that can be a little bit complicated, but I think we try to put the ends together, I believe. I'll have to verify on that, but so far from what I've seen, you put the ends next to each other. I don't know how that breaks the alphabetical rule. I don't know if that's a absolute thing, but here, let me check really quick. Okay, so I think actually there is a correction here. Whenever you have, right, so the way this makes sense is whenever you have 2 groups that are the same, right? So I said n is like a number, and so therefore instead of just simply, so this is 1, 2, this is 1, 2. So instead of having it separate, we have to put, right? So n, and I also have 4, and so this would be N4 diethyl. Okay, and so N4 diethyl and the parent chain, right? So N4 diethyl, yes, hexane amide. There we go. And so this would be the parent right there. All right, now would be the full name. All right, and so the last nomenclature problem here is we have the highest priority group is the cyano, the nitrile group, and so we're going to make this carbon number 1, and then from here we number, so 1, 2, 3, 4, 5, 6. We find the longest chain, so obviously I have to start here. 1, 2, 3, 4, 5. This direction is 5. This direction is 6. So I go in the direction that gets me 6, right? And I don't have a choice where I put the number 1. Number 1 has to be on the nitrile carbon, all right? So on carbon 1, it's the nitrile group, and that's the parent group. Carbon 2, I have an alcohol. Carbon 5, I have the double bond. Okay, so in my naming of this, okay, oh my god, come on. So in the naming of this, I have 2, right, hydroxy, and I have on carbon 2 as well, I have the 1, 2, 3, I have 2 propyl, right? And then aside from that, my thing is a hexane, right? And I have a double bond within there, and yeah, and that's pretty much it. And then as well as on top of that, I have the RNS. And so this is going to be, this alcohol is going to be carbon 1, right? This is going to be carbon 2, right? And then from here, this is longer, and so this side is going to beat this one, and this will be carbon 4. So 1, 2, 3, it goes in this direction, so that's going to be S. Okay, so so I have on this, I have 2S, and so the full name is going to be so I have the 4. 2S, okay, 2 hydroxy, 2 propyl, damn it. And then I don't like putting the number there, so I like to just go, so I have my parent is hexene nitrile. So that's the parent name here. I forgot to put it. Hexene nitrile. You just add nitrile to the end of the word. So hex, right? Hex, and then before the ene part, right? 5 ene nitrile. Okay, so that would be the parent name for this molecule, right? I'll admit nomenclature is not my strongest it's not my strong point, but I feel like everybody can, go through the exams and see the rules for nomenclature quite easily. And she has, pretty clear explanations and rules for the nomenclature. All right, now for the facts. Rank the following compounds in order of increasing reactivity with CH3O-, right? And from lowest to highest rate. And so what we have here is a bunch of esters, and we're going to be seeing the reactivity with esters. And so for this, whenever we're comparing, esters and amides and carboxylic acids and anhydrides and acid chlorides, anything essentially with a leaving group, we're going to be comparing the stability of the leaving group. Okay, so they're all esters. I don't have to worry about that, right? Now I'm simply comparing this O- part. So this is going to essentially, the basic mechanism is that, right? Carbonyl is going to get attacked. This is going to come up. It's going to come back down. Kick this off, right? And I'm essentially looking at the stability of each one of these O-, OR groups, right? And so for the first one, I just have, benzene ring, right, with a negative charge. Whatever, let's pretend that's a well-drawn negative charge. This one, I have the same thing, right? But now I have a nitrogen group here. This one, I have the same thing, except I have a methyl group here. So this is a empty benzene ring. This is a benzene ring with a donating group, and I know it's a donating group because it has a pair of lone pairs on the first atom that is attached to the benzene ring, which is this nitrogen. This can donate inwards this direction, right? And so what we're looking at, right, is we want to delocalize charges. So when we're looking at acids and bases, we're looking at stability of a leaving group or whatever. We're always looking at the stability of the products. So the product here is this O-, right? and I want to stabilize it. And I stabilize charges by delocalizing them across, as much of the structure of the molecule as possible, right? That allows us to disperse the charge, instead of having it concentrated in a single area. And so, of course, I want as much resonance as possible and other things, right? We have a couple of rules that allow us to look at stability of charges, right? So this one I have a benzene ring, it'll resonate with the benzene ring. This one I have a nitrogen, and this nitrogen is a donating group, and it's going to be donating into the ring and therefore pushing the electron density in this direction. What I really want though is to move it in this direction. So this is going counter to what we really want, and so therefore this is going to be 1. This one is also a donating group, but it donates inductively, and therefore it's not through the direct effect of actual lone pairs coming into the ring. It's just the inductive effect of carbon groups. And so this is, kind of it's going in this direction. It's not helping, but it's not hurting as much as the nitrogen is. And so this is going to be 2. And this one will be 3, of course, because this is a neutral, there's no bad, no good. It's just regular resonance in the benzene ring. So this is going to be 3, 1, 2. All right, let's move on. Rank the following compounds in order of increasing acidity. All right. So first things first is to find the acidic hydrogen that we're interested in, right? And to be careful, right? To be extremely careful about how we look at these things. Right. So the first thing might throw us off is that, all right, so I look at the first molecule on the left, and I'm like, okay, I have this dicarbonyl structure. Duh, I mean, I'm looking at this hydrogen right here. This is the hydrogen she wants us to compare, right? That is true. However, she says she's talking about overall acidity of the molecule. So even though she wants us to compare, really she's making it easy to compare a certain acidity of a certain proton, right? She's making us, we have to be careful about also the relative acidities of other things on the molecule. So are there even more acidic protons hanging around? Well, at first glance, we would say that this hydrogen is far more acidic than this hydrogen right here. And that is true. This hydrogen is more acidic than this one. However, this molecule contains 2 carboxylic acids. And so the relative, acidity of, the alpha hydrogen is somewhere, I don't know, it's like 7 or maybe 6, 8, I'm not sure exactly, but it's definitely nowhere near the acidity of a carboxylic acid. And so therefore, this is going to automatically be 3. This is the only molecule that contains the carboxylic acid functional group, and therefore it has the most acidic hydrogen. Carboxylic acid is around, 2 or something like that. Okay? So, when it comes from after this, right, I'm comparing molecule over here and this molecule over here. And essentially, what it comes down to that this is 2 and this is 1. Right? And so this is 2 because this is so what happens when this hydrogen gets removed, right? And this is why this hydrogen over here is less acidic than this one over here. It's for the same reason that this one will be less acidic, is whenever I remove this hydrogen, right, I create a negative charge right here. And so this negative charge is going to resonate, it has 2 routes to choose, right? It's can go into either of these carbonyl structures, right? And so that's 2 resonance. Okay, so now for number 3, rank the following compounds in order of increasing acidity. So, we have another acidity question. This one is also very similar to number 1. And so essentially what we're going to be doing, we're going to be deprotonating, right? So we find the acidic hydrogen. So we have a carboxylic acid. This is the most acidic hydrogen. And so we're just going to remove these. I'm going to imagine these oxygens here with a negative charge. And, we're just going to do that for the remainder of all these molecules. Okay. And then from here, we're going to be observing the stability of these molecules. And so just the same way that this one was done, we're going to apply the same concepts. So I have a negative charge. I want to delocalize it across the molecule. I want to pull it from one end to the other as far and as much as possible, right? And I want to see how well this is done in each one of these. And so we have to characterize, based on the position on the benzene ring, right? So one thing to remember is that the ortho para positions. If I have a withdrawing group on these positions, this equals increased stability. Okay? So this translates to, this translates to increased acidity. Okay? And other sense is increased reactivity. Okay? Can't write, but you see what I'm trying to say. So these things help. All right? So this one is a donating group. This is a backwards donating group, and this is actually a donating group as well. But we have some differences here. All right, so we have 3 donating groups. How do I do this? I have to first find what is the most directly donating, actually donating in, electron density, right? Not just inductively. So first one here, obviously we have this oxygen, we have an ether, right? So this is an actual, donating group that's going, excuse me, going in, and so this is going to be 1, right? Because it's donating in the most, so therefore it's actually pushing in this direction, and we want it to be doing the opposite. So this one's pushing the most, and so this is going to be, hurting our stability, of the conjugate base that forms. And so now comparing the first one and the last one over here. This one is a carbon group. This one's a carbon group that's attached to an oxygen group. So one thing you need to know is that whenever oxygen is attached to a molecule, right, this oxygen is going to be interfering with the resonance, right? So let's say like I had a negative charge over here, right? This oxygen is going to be interfering and preventing the stabilization of this negative charge. So this negative charge wants to go in and resonate with the carbonyl, right? It wants to do all this. However, this oxygen that's attached wants to donate in part of the time, and this will cause this to go up, and this will prevent the negative charge from being able to stabilize. So when the oxygen goes in, essentially, right, it looks like this. And we're stuck with the negative charge over here like this. Okay? So this is the issue with, having, an oxygen or a nitrogen, something with lone pair that's attached to the carbonyl structure. It will prevent destabilization. Why am I talking about this? Well, I want to, talk about the location where oxygens are attached, or, whatever other groups. However, when oxygen is not directly attached, right? So it's not directly attached to a withdrawing group, so we have something like this. Let's say we had this instead, right? This is a different situation. This is not direct attachment, and so instead this actually helps, right? This actually helps the stabilization, because when oxygen is not directly attached, it can't donate in directly. So all the oxygen can do is inductively pull. So now it does the opposite. So instead of donating, the oxygen is now all of a sudden a withdrawing group. And so now the same concept applies over here. So I have a, fully donating. This is donating. However, this is an oxygen that is now inductively is pulling in this direction, creating a partially positive environment, right? So this is going to help stabilize the structure by allowing us to have, inductive pulling in this direction. We have a net pull in this direction. And so this is going to make this 3, and this is going to be 2. I hope that makes sense. Okay? The oxygen is not directly attached, therefore it's inductively pulling, and any inductively pulling is going to help stabilize a negative charge. Alright, number 4, draw the structure of a side product in the Claisen condensation of compounds A and B. Okay, so we have the Claisen condensation of compounds A and B, which is going to look like this. Okay. All right, so we have an ester. Okay, this is the ester. This is the group that the acidic hydrogen is going to be removed from, and so our Claisen product is going to be carbonyl. Ester is gone, right? We have this carbon, right, and we have this over here. So this one, we have this group coming off. This is essentially what we have. So this is the Claisen product, right? Now, the side product is actually just the aldol, right? This can attack itself, right? And so a side product, right? The Claisen product is the main product, side product is the aldol product. So it's if I have this guy, okay, attack itself. And so off of this carbon, I have the OH group, right? And then off of that, that is where I have, have that. Okay, so 1, 2, 3. Very good. And so this is the side product. This is the aldol. Aldol is the side product here. Okay? Alright, so I hope that makes sense as well. Down a bit. There we go. Alright. Now let's do reactions. Okay, so the first question is number one is first step is LDA. Okay, LDA is a strong base, but very weak nucleophile. Strong base, and it's a very weak nucleophile because it is bulky. And so LDA looks like that. Okay, and so it's diisopropyl amine. Okay, and so it's going to abstract from the least substituted side. And so the product of step 1 okay, is this molecule right here. All right. In step 2, we are introducing a primary alkyl halide, and so therefore this is going to attack this off. Okay, so I just redraw my structure. There we go. And then the last step, step 3, this is a primary amine. And so we form the imine, right? So primary amine forms the imine, right? And so we have an R and like that. Okay, so I just take the carbonyl, just copy and paste, make that group, and so it's a CH3. So we just draw like that. 1, 2, 3. 1, 2, blah blah, like that, like that, like that. Okay, easy peasy. All right, you need to know the mechanism for this. Make sure you know the mechanism. All right, so that's simple enough. Okay, now reaction 2. First step is NH3. All right, so NH3, and we have an anhydride. And so what is this going to make? This is going to make one of these into the amide, and the other one is going to be a carboxylic acid. So the nitrogen lone pair on the NH3 is going to come and attack any one of these carbonyls. Okay, and then this is going to be kicked up. Should probably make this thinner. And then this is going to come back down. And then this is going to be kicked off. And so what we get for step 1, okay, is the formation of right? So this is the N. We have to take off one of the hydrogens, NH2, okay? Draw this like that. And so this carbonyl, okay? And then we said this is going to be kicked down, and so this is going to become the carboxylic acid, okay? This is going to become the carboxylic acid. Next step is SOCl2 excess, and so we have two things that this can react with. In the presence of an amide, SOCl2 is going to turn this carbon into the carbon of a nitrile. And so, right, so over here I have this carbon, and this is going to be, right, CN, yes? And then this carbon over here, right, that. This is going to make acid chloride, right? And then the last step, CH32CuLi, that is going to react with the acid chloride only, right? And do what? It's going to make a ketone. So this is just a CH3 group, and so this is my answer. All right? So this is my answer for this part of the question. All right. Moving on, number 3. Step 1, Ag2O, H2O. And so what is that going to do? That is going to selectively oxidize the aldehyde. Okay? And really there's not much you can do over here with this setup. Right? You only have one functional group here really that you have. Nothing too complicated. Next step is COCl2, right? This is often used specifically whenever you have a carboxylic acid group on a benzene ring, but it does the same thing as SOCl2. It just makes the acid chloride. All right. Next step, number 3. Right, we have CH3, CH22, NH. This is going to make the amide. Nitrogen is here. And then this nitrogen group has ethyl. Okay? And then after this step, we have, following this, LiAlH4, then H2O. What this is going to do, this is going to completely remove the carbonyl from this molecule. Okay? And so this is what we have in the end. All right, so it turns an amide into an amine. All right, moving on. Number 4. Number 4, we have this CN. We have H3O plus 200 degrees Celsius. Okay. So what is this going to do? This is going to hydrolyze this CN. It's going to carboxylate it. So this carbon is going to get oxidized. So it's going to become, because this is done in acidic environment and heat, it's going to become a carboxylic acid. All right. And step 2, we're introducing a strong base. Okay. So this is a strong acid, that's a strong base. So all that's going to happen is, right, so switch to line angle, this is going to become O minus. Right? Make sure you put that charge. And then step 3, I'm introducing an acid chloride. An acid chloride is extremely reactive, so this will become a strong enough of a nucleophile at this point to attack this carbonyl. Okay, and so all we have now is the formation of a anhydride. So O, another carbonyl, CH3, and that is our answer. Okay, now the next one, number 5. Number 5 is a retrosynthesis. I could not get it to just align properly for some reason, so we're just going to deal with it. All right, we're just going to deal with it. It's going to look like this. All right, so I need to turn this this reaction here. I need to turn one of these carbonyls. So let's see what changes. So what changes here is I essentially form an enamine on the aldehyde, and the ketone gets reduced. Okay, so what do I do here? Well, one of them gets reduced, and the other is, getting turned into an enamine, right? It's reacting to make an enamine. I have to use a secondary amine. All right. So what my strategy is going to be is step one. Step one, I'm going to be using, right? I'm using a protecting group. All right. I'm going to use the acetyl, form acetyl. So protecting group and H plus, and what that's going to do, that's going to selectively, right, bind to the more reactive carbonyl here. It only works with ketones and aldehydes. Aldehyde is more reactive than ketone, and so this will bind to the aldehyde carbonyl. Right? It'll attack that one, and so this will be left alone. Okay, now that this is left alone, I can perform some reaction, right? And I have to be careful about the reduction reaction that I use, because that has a significant effect on whether or not this protecting group is going to remain, remain there or not. And so I cannot use Clemmensen. I have to use the Wolff-Kishner reduction. And so that's going to be NH2, KOH, and heat. And if you're fancy, you can throw in DMSO. All right, but these are the minimum. Okay, and so this is going to completely take away the carbonyl off of that molecule. All right, so now we're at this, and now what do I have left? Okay, well, what do I have left? I have to get rid of the protecting group. So I have to use HCl plus now for step 3. Okay, this will get me back the aldehyde. And then to get my product, I have to use, this is CH3, I have to use NH, parentheses, CH3, 2 slash H plus. My secondary amine, H plus, I have my carbonyl, this will form the enamine, and that's all there is to it. Okay, easy peasy. If you need to review it, just pause the video and just think about it. Alright, number 6, step 1, I have NaOET, ETOH. I have this, I have an ester, and so I have NaOET, ETOH. I have an ester, and so I am going to be forming Claisen. Okay, so the Claisen is going to occur at the beginning of for the product of step 1. And so Claisen is going to be like this. All right, so this is 1 carbon, 2 carbons, 3 carbons. All right, and so I'm going to choose this one to be the one that loses its ester group. Okay, and attached to it, right, this acidic proton is coming from right here, right? And so attached to it is this carbon right here. This carbon has, coming off of it, right, a carbonyl group that has an ester that has 2 carbons. And off of this group is this carbon and the cyclohexane. Okay, so this is the end of, this is the, not the end of step 1. We still have a part left. And so at the end of every Claisen, you have to be careful. At the end of Claisen, we're going to be forming this dicarbonyl structure. Okay, and so we're going to be forming the beta dicarbonyl structure. And so this is going to become a much more acidic proton, right? And so I'm still in the presence of my base, and so this is more acidic now than what I started with. And if this got deprotonated, then this is sure as hell is going to be deprotonated. And so the end of step 1, right, you have to show this. This is the actual end. You don't have to show this one, but you have to show this one. So the end of step 1, after I redraw this whole thing, okay, is going to be this structure right here. All right, just try to make that clear. All right, this negative charge. And then this negative charge is going to be what is used at the end of step 2, for step 2 to attack the primary alkyl halide. All right, and so step 2, after I redraw this one more freaking time, okay, all right, so this is adding 3 carbons, 1, 2, 3, and off of here I have 1, okay, and then 2. Okay, so this is what I have. I know it looks crazy. And then the last step, number 4, this is H3O plus 180 degrees Celsius. This is the decarboxylation step, right? And so I have a dicarbonyl structure, and one of them is an ester. So I have to, my requirement is that I have to have something that is either oxidizable up to a carboxylic acid, or I have either ester or a carboxylic acid. Okay, and so end of step 4, I'm going to have this whole thing, except this whole part is gone. Okay, and so the answer for step 4 is going to be this carbonyl. Then we have 1 carbon, right? And then 1, 2, 3. So 1, 2, 3. And off of here I have 1. There we go. Okay, so this is our answer. This is my answer over here. Okay, so the last part is just the removal of the ester group completely. This will be first turned into a carboxylic acid, right? Because you have HCl plus, I have an ester, I have heat, that's going to make this a carboxylic acid. Then the carboxylic acid will bubble out as CO2. Okay, and all that will be left with is this carbon right here and this ketone. All right. Now let's move on a bit. All right, mechanism time. So now we're on mechanism. Mechanism, we have to form from this molecule. I'm forming this, and so essentially, I need to basically do the reverse of an acetyl reaction. And I told you guys you need to know how to do this. So the first step is to choose either or of these oxygens, okay, and to attack H2 plus. So I'm just gonna fill in what she has over here already. On already has, this is on's key, right? H2 plus is right here. This is going to attack H2 plus, and we're going to do this, right? So the first step is this. Okay, this will become OH plus right here. All right, make sure you just show all your charges. Okay, and so at this point, we form the leaving group. Okay, and so what happens after this is water will come. Yes, water. Okay, so water is going to come and attack this carbon, and this will get kicked off. Okay, and so I'll have this oxygen. Okay, and then over here I'm going to have, right, I'm going to have that. Okay, and this is what was just kicked off. Right, this alcohol group is now formed. All right, let's count my carbons. I have 1, 2, 3. Okay, so I'm in the clear here. 1, 2, 3. That's all I need. And so now the next step is the deprotonation. So I'm gonna use water again. Okay, this should be pretty straightforward. Okay, so now I have an OH group right here, and then this is connected to 1, 2, 3 OH. Okay, so 1, 2, oops, 1, 2. All right, 1, 2, 3. Okay. Yes. All right. All right. So at this point, what do I do? So my goal is to also separate this side and just repeat the same steps. All right. And so I just have to repeat these steps and basically just rinse and repeat, rinse and repeat over and over and over. Actually, I made a small mistake. So I made a small mistake here. I need to quickly fix some of this stuff. All right. My mistake. Okay. So what was my mistake? Well, my mistake was actually that my mistake was that the first thing that happens is the same, right? So this gets protonated, and when this gets protonated, instead of the water, another water coming to attack, right? That's not what happens. What happens first is that I look for intramolecular stability. That's what happens first. So I already have an oxygen that is here. And so this oxygen is going to donate a lone pair in to push off this leaving group that forms here. And so this is going to form a carbonyl-like structure as seen here. And over here, you can show a resonance structure for this. I always show the resonance structure, but in the instructions it says you only have to show the major contributor. And so this is already the major contributor, so you don't have to show the other one. But I usually always show it just for, that's how I like to do it. And so when you form this, right, this happens because this is much more readily occurs, and this donates in, helps us leave. And then once this forms, right, I move the positive charge to over here. This is a carbonyl-like structure. The water attacks this structure, and then I get this gets its electrons back, and I get this water here. And so this water is positively charged. Okay, and so now you know what happens here. And I left the old one on the bottom here so that you can see how this is different, just so you can compare, right? I'm going to take off one of these hydrogens, give it back to the oxygen, and we get this. Right? And then 1, 2, 3, like that. Right? And so after this step, what happens? Well, after this, right, I have to keep going in the mechanism. So I need to bring back, I need to repeat the same thing on the left side. So I did the same, the stuff on the right side. Now I have to repeat it on the left side. So I get this. Okay. And so at this point now, this alcohol group is going to contribute a pair of electrons in here, right? Oops, not there. It's going to contribute into right here. And this is going to get pushed off right there. Okay. And, all right. So at this point, all right, so I have this. It's going to donate in. I'm going to get something that looks like this. Right. So now I get this OH group. I get this. Right. Okay. And so now all I need to do now is to deprotonate. And then I get my answer. All right. So that's nice. All right. So not too bad. All right. Now let's do the synthesis. All right. So the synthesis says that synthesize the molecule below using any of the following reagents: benzene, any alcohols with 3 carbons or less, and any inorganic reagents. All right. This one's actually a pretty easy one to do. Okay. So what I need to realize is the first step of any of these synthesis problems is to look at the what kind of product do we have, and we have several products that we can identify. You can say I have enamine, I have imine, I have the alpha beta unsaturated product, I have the beta hydroxy ketone or whatever, I have the Michael product, I have the Claisen product, whatever, right? I have the aldol product, right? This is right here. This is a alpha beta unsaturated ketone. And so here I have the ketone. This is the alpha position, and this is the beta position. Okay? And so if my alpha beta position has a double bond, right, in between the alpha and beta, I know this came from a aldol reaction, and it had heat involved. There was heat. And so the first thing that I can do is I can do the heat step, right? The heat step will allow me to go back to the group with the alcohol, right? This is me gearing up to do the aldol reaction, just to show everything more clearly. So I'm going to skip now. I'm going to start doing line angle if you don't mind. And so what we have is this is going to have the beta always has the alcohol group on it. Okay. Here we go. So I'm just going to drag this. All right. So I have this now. And so now how do I make this? So I have the alpha position, and I have the beta position. Okay, and so the alpha position is the position, the carbon there was the one that attacked, and the beta position is an alcohol now because that originally was a carbonyl. And so what I have from before, I use NaOET, ETOH, that's what I use for my aldol. And so I have on one side I have this, and on the other side, right, need to be so long. This is what I have. Okay, so this is going to be the thing that gets deprotonated, right? And this is going to come and attack this one, right? So I hope everyone can see that. So now let's form the left side because it's easy. Left side is just an aldehyde on a benzene ring, so I use CO, HCl, CuCl, Al, Cl3. This is an old Orgo 1 reaction, Orgo 2, just 2 reaction. And this will give me back the benzene ring. Very easy. On this side, how do I make this? Well, all I have to do is use AlCl3 on the arrow. This was a very easy synthesis. There are much harder ones. Sadly, I'm not doing a harder one. And I go back to an acid chloride plus the benzene ring. Now to make the acid chloride, so Cl2. Carboxylic acid. And so now this is a 1, 2, 3 long carboxylic acid. I don't have to worry. And now I can just do Jones. Right? And this will give me 3 carbon long alcohol, which is what I'm allowed to go back to. Okay? And so we are in the clear now. All right. And now the spectroscopy. All right, that was a very easy synthesis, honestly. There are much longer and more difficult ones. But generally, this is a good example of the aldol reaction, which you guys should be prepared to know how to do. All right, so it's pretty marked up, but I'll try to talk about it without you guys seeing too much. So let's just, first things first, unsaturation number. All right, 12 times 2, so that's 24, plus 2, it's 26, right? So 24, 26, right, minus 14, right? So that's going to give us 12, right? And then divided by 2 equals 6, okay? Okay, so our unsaturation number is really freaking high for this problem. So it's 6. My formula has 2 oxygens in it. I might have quite a few things in here that are sneaking around. So let's see. So I have I definitely have a benzene ring in here. So let's just take a look at the spec graph. And so in the 1600, the 1700, I have a peak, and then around the 1650, I also have another peak. And so I likely have a carbonyl, and maybe I'm not sure about the other one, but maybe also an alkene. Okay, so I need to be looking for these structures to be confirmed in the NMR. All right, And so I can look at the NMR now, and in the NMR, I'm going to, since I have a high unsaturation number, I'm going to start looking at the 7 to 8 region. And in the 7 to 8 region, I see a 5H peak, and that indicates to me that I have a mono substituted benzene ring, which will account for 4 of the unsaturation numbers. And so that leaves me with 2. In the 5 to 6 region, I see here that I have a single peak, and so that indicates to me that I have a double bond that has one single hydrogen on it, okay? And this hydrogen is not next to any other carbons. And so that means that this carbon right here, so these carbons right here and this carbon right here, they have no, there's no other other direct carbon hydrogen attached to it. Okay, that means there's no hydrogens obviously on this side, right? And that means that this carbon is not attached to something that has hydrogens on it over here, depending on where the hydrogen is. Okay, so I have this, and then after this, I have in the 4 region, I have a CH2 peak. So that means I have a CH2. And this CH2 is, I'm going to put it in a box because I always box the things that are corresponding to the integration value. This is attached to some O, and it's also attached to, it looks like 1, 2, 3, 4. It's likely attached to a CH3. Okay, so I have that. And then I have a lone CH3 peak. Okay, and then I have another CH3 peak, right? And this CH3 peak is 1, 2, 3. So that is attached to a CH2, right? So 3 minus 1, that's CH2. And so now I have to piece all this together. And if I try to piece all this together, one thing is very important. Whenever you have O2, I want everyone to always check in between the 160 to the 180 region. And so I check the 160 to 180 region, and I see a little peak over here. And what this peak indicates to me, right? This indicates that I have an ester. What do you look at that? So this peak tells me that I have an ester. And so that's what On has figured out, right? So I need to consider all these things. I have an ester, I have an alkene, I have a monosubstituted benzene ring, I have a CH2 that's next to an oxygen, and it's next to a CH3 probably. I have a lone CH3, and I have a CH3 that's next to a CH2. So first things first, these two are probably the ones that are next to each other, right? This is probably somewhere else that's by itself, and this is, obviously I don't have much of a choice where this is located. So if I start building my molecule, I start from the benzene. Well, it's actually more wise to start from the double bond in this case because the double bond has four bonding points, and I have a hydrogen here, and then I need to consider how I bond things off of this. So I have a hydrogen here, okay, and so this hydrogen, it's a lone hydrogen, and so I have to have 4 things coming off of this double bond. One of the things is going to be this benzene ring. And remember, guess and check. Do what you think. Do what you think is right, and then you can check it by cross, looking back at what we have and seeing do the graph support this hypothesis. And so this is what I'm formulating at the moment, and I'll go through my logic in a second. All right. So this is the correct answer. I'm 100% sure. Right? I'm very sure that it is. Um, And by the way, you can switch the location of, trans, cis. I don't think you need to know, is it trans or cis. I don't think there's enough information to let you know what it is. But um, anyways, so I have a double bond, and this double bond has a single hydrogen on it, and it's not connected to any other carbon that directly has hydrogens on it. Okay, so off of that means that this carbon right here, obviously we know it doesn't have any hydrogens, so that takes care of that, and we know that whatever is coming off of this carbon right here, right, this R group, it has no hydrogens. And this is the only way to ensure that this location is a singlet. Okay, and okay, so that's the only way to ensure that this location is singlet. And so I'm going to start building my compound centered around that thinking about that. So excuse me. So I have the double bond, and so I'm going to attach the benzene ring coming off of this double bond. I don't have another place for it, and we can talk about if it could possibly fit anywhere else. I have another location that needs to be, I have two more locations that need to be filled up. One of those is going to be filled up by a lone CH3. The other one is going to be filled up by the ester. And so the ester has to fit here because we said this is a lone H, and the only way that we can have a lone H in this location is if I either have the benzene ring or the carbonyl ester in this location. Both of those would provide a situation where we don't have any hydrogens on the adjacent carbon. Okay, so um, so this takes care of this aspect. Then the C13 NMR gave us enough information to tell us that we have an ester group, and so I know this is going to have to be the carbonyl, and so that means that the oxygen is here. We have a CH2 that is connected to an oxygen, so the CH2 goes in that location as we wrote over here. And we also have a CH3 that we hypothesize is next to it. And this is supported by the fact that we have a CH3 that is, we have a CH3 that is next to a CH2. And so that's where this is going to be. Okay, so if we try to put any of the other groups in any other location, you'll find that it simply does not work. I am forced to have 3 R groups coming off of a double bond, and so therefore the only thing that can feasibly, possibly work is that if I have all these groups in this location, like this. And so benzene ring will not be able to fit anywhere else because it is mono-substituted, and therefore the only location that has the bonding to allow the benzene to attach is the double bond. I cannot have it attached to anywhere over here, right? This has to be attached to an oxygen and the CH3. So not over here. This is a lone CH3. This is the only location. And so all that remains is that whether, is just making sure that this location here, this carbon and this carbon have no hydrogens on it. So over here and over here. And that's essentially the logic for the NMR and spectroscopy. Most important thing is the usage of the C13 NMR 160. So you'll have the 160 and the 180, and in the middle you should see a little peak, and that should give you the information that you have an ester. Very, very helpful, right? If I didn't have that information, maybe this wouldn't have been that much harder, honestly, but it clears up some things very nicely. So this is the video for exam 2017, and I hope it helps, and just some final reviews, some final concepts to go over before the exam. I wish everyone the best of luck, and I apologize this is so last minute, but you do have all of Friday after all, so hopefully this is able to help a sizable amount of you guys. Anyways, best of luck, and wish you the best.